So formally speaking, what is the method of least squares? The method of least squares is to find a function, let's call it f, from within our family of functions, whatever that family happens to be. In this case, that family we're calling f1. It's the set of all linear equations passing through the origin, y equals mx. And least squares means the following. Find an f such that the difference between f, let's say f of x, and the x-coordinate of each of our data points. So if I say this is x1, x2, and x3, or 0, 2, and 4 in this example, if I take that difference and I square it, so that's where the squares part comes in, and then I add those all up, then this quantity, I have 3 data points, so that's going to be a sum I equals 1 to 3. Then this quantity tells us how far away our function is from each of our data points. So last time when we did this process experimentally, that quantity, the summation of the differences squared that we have on the left-hand side of what we have right here, that's the quantity that results just from subtracting the value of our function from the x-coordinate of each of the points in our data set. So, for example, this distance would be, what would that be? From -2 to 1, so that's 3. This distance right here would be 1. And this distance over here is also 1. If I take those differences and I square them and I add them up, 3 squared plus 1 squared plus 1 squared, I get 11. And that 11 is what we call the squared error, right? It's the difference between the value of the function and the x and the y. So we take the differences between the line and the data points, the y differences, we square them, we add them up, we get the squared error. And that is the quantity that's on the left-hand side of this definition that I'm working on here. Here we go. And the fact that we're calling it least squares means that what we're trying to do is we're trying to find, as you did with the Mathematica applet on Monday, the smallest possible value of that error. So what we want is to find the minimum value of this from among all the functions in our space of functions that we're working with. So actually, how do I want to say this? I want to say that the error, so this left-hand side is the error committed by f, the squared error by f. And that, in the least squares formulation, is supposed to equal the minimum from among all functions, let's call them g, in our family of the sum, I equals 1 to 3, of the difference between g of x. And actually, I don't want xi here, I'm sorry. I want yi. G of x minus yi squared. So this is just the fancy way of saying that we're looking for that function for which the total amount of squared error is the minimum possible from among all functions in our family. So it's least because of the minimum, it's square because we're squaring the error when we add them together. How did we do this process? How did we find this minimal function? Matrices stuff, linear algebra, exactly. What in the beginning looks like a problem that might be a calculus problem because we're minimizing something, has an elegant solution in linear algebra. And to get there, all you do is you try plugging in your points into the functions that you're trying to fit to, and in the process, getting an over-specified system of linear equations. So in this example, if I have a function y equals mx and I want it to pass through all three of these points, then in order for it to pass through the point 0, 1, for example, we would need 1 to equal m times 0. And already you can see that's a problem, right? Because on its face, it's going to give you a system of equations which is inconsistent. But never mind that. Let's forge ahead. 2, 2 is going to give you another equation. 2 is equal to m times 2. And then finally, 4, 5 will give us an equation. 5 is equal to m times 4. So you end up with these three equations, and in this example, only one unknown, m. Right? So this is way overspecified. Chances are there is not going to be an m which solves all three of these equations. So what do? If I rewrite this as a matrix equation first, it would look like 0, 2, 4 times m equals 1, 2, 5. And that equation very clearly has no solution, because what's on the left-hand side is always going to be a multiple of the vector 0, 2, 4. And the thing on the right is clearly not a multiple of the vector 0, 2, 4. So that equation has no solution. So what do? What's the trick that has always availed us so far this semester in turning something which doesn't have a solution? Multiply by the transpose. Exactly. Transpose of what? 0, 2, 4, right. So we'll just transpose 0, 2, 4. We'll multiply by it on the left, and if I multiply by it on the left, then I also have to multiply by it on the right. Slide this over. 0, 2, 4. And in doing so, we're going to change this into a system of equations which does have a solution. But the problem is that its solution is not necessarily going to exactly solve the original equations. Instead, it's going to be the best possible solution to the original equations, right? It is the solution which minimizes the total squared error that we can have, because it's the same equation that gave us the projection, which also minimizes the squared distance from a point to a subspace. So 0, 2, 4 multiplied by 0, 2, 4, that's going to be 20, I think, if I'm doing my arithmetic right. 20. And then on the right-hand side, 0, 2, 4 times 0, 2, 5 is going to give me 24, I hope. And so now you know what the slope of this best fit line is going to be. Yeah, 24 over 20, or 6 over 5. So that line, which passes through the origin, which best fits these three data points, is the line y equals 6/5 x. So we just did the first part of question 4 together. One of the things that makes this problem a little nicer than the problem of projection is that we actually care here what the value of m is. The solution itself tells us what we need to know. If you recall, when we were doing the projection problems, if I can just borrow a blank screen here for a minute. When we were working on projection problems, just to get it set up again here, we had a subspace, S, and we were trying to project points onto this subspace. And the subspace lived in some vector space, whatever. I'm going to draw it as though it's R3, but it doesn't have to be. And if I want to project this point B onto the subspace, then ultimately what I cared about was, here's P of B. Ultimately what I had to do in order to make this happen was create a matrix whose columns form a basis for S, and in doing so, I end up pulling back to a vector space of a different dimension that has the same dimension as S rather than the same dimension as the space in which S resides. So I pull back into a two-dimensional space, and I decide to find some point back here, X, such that PB was equal to AX. But all of this is a long roundabout way of saying that when we set up the normal equations, right, because we couldn't solve AX equals B, so instead we had to multiply both sides by A transpose and settle for these things called the normal equations. That when we solved A transpose AX equals A transpose B, in the projection case, the solution gave us a point back here, x, but we didn't ultimately care about x. Instead, what we cared about was A times x. Right? The solution that we got was not the ultimate thing that we cared about. So in the projection case, the solution of the normal equations was not interesting by itself. X is not interesting in its own right. But AX was. But in the case of finding our least squares equation to fit a line, the solution to the normal equations is very much interesting by itself. This m, in other words, that we got here in the process. That m, our solution of these normal equations, was exactly the slope parameter of our equation of best fit. So that's kind of one of the nice things about equations of best fit as compared to projection problems, is that once you solve the normal equation, which is what we got down here, its solution by itself is meaningful. Its solution is the coefficients of your equation of best fit.